itself as well as protein binding. We're going to really get into the determinants of volume today and dig deep and try to find a model for the volume of distribution at steady state. We've talked about rate of distribution, and now we're into extent of distribution. We had an introduction to VC, our central compartment volume, which is what we use to determine loading dose. And then we also talked about apparent volume of distribution. And today we're going to kind of dive deeply into steady state volume of distribution. So our volume of distribution at steady state is just that. It's the volume that the drug occupies in your body once you have reached steady state. So this is once you've actually, the drug is getting where it's going and you're in a state of equilibrium. So here's the model we're going to use, and I don't want you to worry too much about it, but all these numbers and everything, but the idea that we have a plasma compartment, so if you get something IV, or if you take something by another route and the drug eventually makes it to your plasma, or your bloodstream, remember the highway of the body, it's going to start in this plasma concentration, right? So, and then, so we've got our volume of our plasma times the concentration of the drug in the plasma, which will give you the amount of drug in this particular space, or compartment that we like to call it. This is just a mathematical rendering of what's going on. That drug will then, in some amount, travel to the rest of the tissues in the body. And the rate of its movement from the plasma to the tissue we are calling K1. So it's moving from the plasma to the tissue. Then we have a volume of our tissue times the concentration of the drug in the tissue, which gives you the amount of drug in the tissue. This is a reversible process that will then, the drug will travel then back to the plasma because it has to be in the plasma to be eliminated from the body, right? So the amount of the drug in the body is going to be equal to your plasma volume times your concentration in your plasma plus your tissue volume times your the concentration of the drug in your tissue times your this rate of exchange between your fraction unbound in your plasma and fraction unbound in your tissue. So don't worry about this too much. This is actually the derivation for the eventual equation that we're going to be using. Don't worry about the derivation. I just wanted to show you the math. Okay, so this, I think, is a much easier rendition of what is actually happening. So this is your plasma compartment. This is your tissue compartment. Drug will be introduced to the plasma, and it will either be bound to plasma proteins or it will be unbound from plasma proteins. Now, remember, plasma proteins are proteins. Proteins are relatively very large molecules. They have a very large molecular weight. Drugs have a much smaller, in general, have a much smaller molecular weight. Drugs have molecular weights in the 300 to 500 range, and proteins are in the tens of thousands usually. So I usually think of this little drug being bound to a big honking molecule, which is the protein. So because that drug is bound to a protein, it's not going to be able to easily move through the membranes to get between plasma and other tissues. So if it's bound, it's unable to move from this compartment. If it's unbound, however, and moving around on its own, it can move through the membranes to the tissues. Then once it gets to the tissues, it can be bound to proteins in the tissue. So once it's bound to proteins in the tissue, once again, it cannot move back into the plasma. It has to become unbound in order to move between the two compartments. Oopsie, I didn't mean for that to happen. And again, this is just a derivation of the equation. So our volume of distribution at steady state is going to be equal to the volume of our plasma plus the volume of our tissues times the ratio between the fraction unbound in our plasma, if you want to think of a P there, fraction unbound of the unbound drug in the plasma over unbound drug in the tissue. Now let's talk about that equation a little bit. So here's the same equation. And if you think about, okay, this is going to be a pretty fixed amount here. We know this is about 3 liters in a 70 kilogram person, or 0.04 liters per kilogram. This stays pretty constant unless something bad happens, right? Like if you lose all your plasma, which is not really compatible with life. So, and then you also have a fairly fixed volume of your tissues here, which is 39 liters in a 70 kilogram person, or 0.56 liters per kilogram if you need to weight adjust it. So the things that are going to be changing are the fraction unbound in plasma and the fraction unbound in tissue, which is what will determine your volume distribution at steady state. Now, and again, if you add your volume of plasma and volume of tissue together, you will get your total body water, which again is in a 70 kilogram person is 42 liters, or 0.6 liters per kilogram. Now let's think about this for a minute. So the two things that are really changing are your fraction unbound. Where's my little pointer guy? I don't see him. Oh, okay, there he is your fraction unbound. Let me change this to a pointer. Is your fraction unbound in plasma and your fraction unbound in tissue. So let's think about it. If your fraction unbound in tissue goes up, okay, that means that there's less bound drug. Your fraction of your drug that's not bound to a big honking molecule is larger. So that makes it so the drug can move freely between the plasma and the tissue compartments. Now, look at this. Our plasma compartment is only 3 liters of the 42 liters. It's a very small percentage. So the plasma volume is very small in relation to your total body water. So if your drug is highly bound in the plasma, it can't move out of this very small compartment. It's stuck in this very small compartment. So you're going to have a relatively small volume of distribution. However, if your fraction unbound in plasma increases, now more of it's free, so it can move around in the body more, and therefore your volume distribution will increase. If the drug becomes more highly bound in the plasma, the opposite would be true. Now you have to balance this because it's not just about fraction unbound in plasma, but it's also about fraction unbound in tissue. If your fraction unbound in tissue is very high, that means that the drug is not highly bound in the tissue, so it can move easily back into the smaller plasma volume, and therefore your volume of distribution will decrease. If your fraction unbound in tissue is very low, which means that it's very highly bound to tissue proteins, then your volume of distribution is going to be very large because it's stuck out there in that large tissue compartment. This is the major idea we're going to be working with in the workshop. So if you don't get it yet, hang on, we're going to be working with this concept. It's the most important concept here, I think. So that's just an introduction. Okay, so here's another example. So if your fraction unbound in plasma and fraction unbound in tissue are equal to 1, that means they are equal, right? The fraction, it's as highly bound in the tissues as it is in the protein. So this will fall out. This will become 1, and your VSS will be equal to your plasma volume plus your tissue volume. Excuse me. Oh, pardon me. Okay. So your volume distribution will be your plasma volume plus your tissue volume. And I make your total body water as kind of like a middle volume of distribution. If it's smaller than total body water, then it's a relatively small volume of distribution. If it's larger than total body water, then it's a relatively large volume of distribution. Okay. So what if your fraction unbound in tissue in plasma over your fraction unbound in tissue is less than 1? So what does that mean? That means that the fraction unbound in plasma is less than the fraction unbound in tissue. So if your fraction, I have to change it to bound for me. So if your fraction unbound in plasma is less than your fraction unbound in tissue. That means that it's more highly bound in the plasma than it is in the tissue. So it's more highly stuck in that small compartment. So you're going to have a relatively small volume of distribution because it's stuck in that small volume in the plasma. If the other case is apparent, so if your fraction unbound in plasma is greater than your fraction unbound in tissue, so that will make this whole thing bigger than 1, well, we can see mathematically it's going to make a large volume of distribution, but let's talk through it. This means that the fraction unbound in plasma is greater than the fraction unbound in tissue. So the fraction unbound is greater, so there's less bound in the small compartment and more bound in the large compartment, in the tissue compartment, giving you a larger volume distribution. I have to think through it and change it to bound where it's bound, but you know, whatever works for you.